Good evening. Today we are going to start with the fifth chapter, Magnetism and Matter, which is in your NCRT textbook. This is actually a continuation of the fourth chapter, Magnetism and Moving Charges. And this must be very familiar to you, where we derived the equation for magnetic field along the axis of a circular current loop. Remember this one? We had a circular current loop like this, which carried current, and axis would mean a line passing through the center and perpendicular to the plane of the coil. Using Biot-Savart law, we derived the expression for magnetic field at point P because of the current in a circular loop, and that we got as B, which is the axial field. It is along the axis, given by the formula mu 0 I r square by 2 into r square plus x square the whole raised to 3 by 2, where r is the radius of that circular coil carrying current, x is the distance where you are finding the magnetic field from the center of that current loop. Okay. Now the direction of magnetic field, this is a magnitude here, and the direction was given by the right hand thumb rule, where I told you if your current is here in the anti-clockwise direction, the magnetic field is perpendicular to the plane of the coil and outwards, and if it is in the clockwise direction, the magnetic field is perpendicular to the coil and inwards, given by right hand thumb rule, where the curling of your fingers will give you the direction of current, thumb will give you the direction of magnetic field. Okay, now this circular loop we know has a magnetic field. So if it has a magnetic field like this coming out, then naturally this is a north pole and this is a south pole. So every coil that carries current, if your magnetic field is like this is north end and that is the south end. So it is having a north pole and a south pole separated by distance, and that is what you call as a magnetic dipole. So we already know this circular coil is behaving like a magnetic dipole. Not only that, in the previous chapter, remember we did a derivation where we have a rectangular coil which is carrying current in the clockwise direction, and we found out the torque acting on it as mb sine theta, which is tau equal to m cross b, and we said this is very similar or analogous to our equation tau equal to p cross e, which we did in electrostatics. And since these two equations are analogous, we then came to the conclusion that this is a torque acting on an electric dipole, and therefore here the torque given by this equation is a torque acting on a magnetic dipole, which means that this coil that is carrying current behaves like a magnetic dipole. So we have already come to the conclusion that any planar loop, irrespective of the shape, because we said this n is what? NIA. So it is NIAB sine theta. In the formula, we are not interested in the shape of the loop. We are only bothered, the formula only talks about the area of the loop. So whether it be rectangular or circular, any planar loop, irrespective of the shape, behaves like a magnetic dipole. From this it is very clear. So we already know that a planar loop which carries current behaves like a magnetic dipole. Now this chapter, Magnetism and Matter, starts with the first topic, which is asking you to prove or show that a circular loop like this carrying current is a magnetic dipole. We already know it, but you need to prove and show that it is behaving like a magnetic dipole. So I've taken this formula, mu 0 I r square by 2 into r square plus x square the whole raised to 3 by 2. Now if you take this point P far away from the center of the axis, you may take x much greater than the radius of the coil, which means in the denominator it's okay to neglect this r, because here it is r square plus x square. If r is very small compared to x, let's say if r is just 0.1, square it becomes 0.01, and then it becomes negligible to x because x is very large, and therefore we may write B axial in that case will be mu 0 I r square by 2 into, I have neglected the r square, x square raised to 3 by 2, the 2 and 2 will get cancelled, and we have x cube. Now if you remember, the constant in magnetism is mu 0 by 4 pi. So I need to get that mu 0 by 4 pi here. I only have 2 here. So I need to have an extra 2 pi in the denominator, because then I'll get the 4 pi. So I multiply and divide by 2 pi so that I don't change the value. Now I may write this as B axial equal to, you can see that. I may write this as B axial equal to this mu 0, 2 into 2 pi, I'll write it as mu 0 by 4 pi. Then this pi r square, you know, will be the area of the coil. So this I into pi r square I will write as A into 2 by x cube. This I into A, last chapter we discussed magnetic dipole moment as NIA. Remember, magnetic dipole moment is NIA. If the number of turns in this coil is 1, then magnetic dipole moment of that singular coil will be I into A. So this I into A. So this is B axial equal to mu 0 by 4 pi and 2 into magnetic dipole moment M divided by x cube. M is a vector, will have the same direction as magnetic field along the axis, because if you remember, I told you magnetic field is given by the right hand thumb rule. So if it's carrying current in the anti-clockwise direction, the magnetic field of this coil is outwards. M, this is a scalar, this is also a scalar. The only vector here is the area vector, and the area vector will decide the direction of magnetic dipole moment. Area vector, you already know, will be perpendicular to the plane of the coil, and if the coil carries anti-clockwise direction current, it is perpendicular and outwards. So you see, this B axial and the magnetic dipole, which has the same direction as area vector, are in the same direction, and so this is the B axial of a circular loop if you take x much greater than r. Now this is very similar to the dipole E axial. Remember, in electrostatics, for dipole we derive two equations, E equatorial and E axial. In that E axial, the formula was 1 by 4 pi epsilon 0 2p by x cube, where p is the dipole moment and x is the distance from the center of the dipole to the point along the axis where you are finding the magnetic field. So if you compare these two equations, you will see they are analogous to each other. The constant 1 by 4 pi epsilon 0 replaced by mu 0 by 4 pi in magnetism. Here x and x. There x is the distance from the center of the electric dipole to the point along the axis where you are finding the electric field. Here x is the distance from the center of this dipole to the point P where you are finding the magnetic field, which is along the axis. Then the 2 is there, magnetic dipole moment. Here it is a electric dipole moment. So since the two equations are analogous, we come to the conclusion that a circular coil that is carrying current also behaves like is a magnetic dipole. So that's the first topic in this chapter for you, magnetism and matter. The next topic that we have in this chapter, they're asking you to derive an expression for the magnetic moment or dipole moment of a revolving electron. In an atom, you know that we have the central nucleus, and in orbits, circular orbits, we have electrons revolving around it. This is the radius of that orbit. Okay, and you also know moving electrons constitute current. So if you look at this electron in circular motion actually is like a circular coil that is carrying current. And if it is a circular coil carrying current, it behaves like a magnetic dipole. And we are now going to find out the dipole moment of that revolving electron. Now magnetic dipole moment is what you need to find out. We know that it is I into A because the number of turn here, single orbit, I have taken n as 1. Now I am going to replace this with mu L because in the final equation for the dipole moment of an electron, we have one more m which represents the mass of the electron. So then later there will be a confusion because if you use m for dipole moment and m for mass of electron, then there will be a confusion. So in your textbook, we are using mu L as dipole moment of electron. Now I, you know, is q by t into A because rate of flow of charge, q by t into A. Now here this time period t is distance by speed. The distance covered when the electron completes one revolution here is 2 pi r divided by the speed, that is v, which is what you call as time period. Time period is the time taken for the electron to complete one revolution. So here we have 2 pi r divided by the speed giving you the time period. Now what I'm going to do here is mu L is therefore equal to Q. I'm going to replace with E, which is a charge on an electron. This time is taken as a time period. So this will be 2 pi r. The V will come on top. Then area here enclosed here will be pi r square. So if I cancel this and this, I have the expression for mu L as EVR by 2 pi. EVR by 2 pi. Now I am going to multiply this with m and divide by n so that I don't change the value, so that I may replace this mvr with angular momentum. Last year in rotational dynamics, that is in class 11, we learned the angular momentum as r cross p, which is r into, this is linear momentum, mvr, and so L mvr, angular momentum is mvr. So I may replace this as mu L is equal to E into mvr. I will replace with the angular momentum divided by 2 pi m. Okay. Now here, if I bring L to the left hand side, we have mu L by L is equal to E by 2 pi m. E by 2 pi m. Okay, this pi got cancelled. Yeah, I'm sorry. This pi has E by 2m. E by 2m. Okay. Now here, this is called the gyromagnetic ratio. Gyromagnetic ratio, defined as the ratio of the dipole moment of the electron and the angular momentum of the electron in that orbit. So you will see that E, the electronic charge, which is 1.6 into 10 raised to minus 19, m, the mass of an electron, which is 9.1 into 10 raised to minus 31, both of them are constants. So the ratio between mu L, which is the dipole moment of the electron in that orbit, divided by the angular momentum of the electron in that orbit will always be a constant, and that constant is what you call as gyromagnetic ratio. What we want actually is the dipole moment, expression for dipole moment of the electron. So we go back to the dipole moment of the electron as, from here we know mu L is equal to EL by 2m. Bohr's second postulate. I'm sure you've learned, I'll be teaching you Bohr's postulates in the chapter atoms, but I'm sure you've come across Bohr's postulates in chemistry last year. The first postulate, which tells you that the electrons can only revolve around in orbits which are called as the stationary orbit or stable orbit. The second postulate of Bohr says, or he defines this stationary orbit or stable orbit as an orbit where the angular momentum of the electron is an integral multiple of h by 2 pi. So these orbits, which are called stable orbits or stationary orbits, in those orbits the angular momentum of an electron will be integral multiple of h by 2 pi, where h is Planck's constant. So I'm going to substitute that here so that I get mu L is equal to E by 2m into nh by 2 pi. And we get that as NEH by 4 pi m. Suppose I take n equal to 1, that is the first orbit, then the dipole moment of the electron mu L is equal to EH by 4 pi m, which again you will see all of them are constant here. E, the electronic charge, H, which is Planck's constant, 4 pi, and m, the mass of an electron. So this whole thing is a constant, which is called as the Bohr magneton. It is called Bohr magneton. So Bohr magneton is defined as the dipole moment of an electron in the first orbit, because we took n equal to 1. So this is the derivation for the dipole moment of an electron. So that was the second topic in your textbook. then what we have here, see, when we discussed magnetic dipoles in the last chapter, the fourth chapter, I told you that a bar magnet with a north pole and a south pole is a magnetic dipole. Similarly, the solenoid that you learned in class 10, solenoid also when you pass current has a north pole and a south pole, so behaves like a bar magnet. It is also a magnetic dipole. And in this class 12, chapter 4 and 5 together, we have just seen that any planar loop that carries current will behave like a magnetic dipole. So the third topic in your textbook for this year, that is magnetism and matter, they are asking you to show that a solenoid, that is a bar magnet, which is an equivalent solenoid, will behave like a magnetic dipole. So we take a solenoid and show that it is also behaving like a magnetic dipole. So in this derivation what we have is, so we're going to find out bar magnet as an equivalent solenoid. That is, bar magnet is a dipole. The equivalent solenoid also behaves like a dipole. So we are now taking a solenoid with capital N turns. So it has got N turns, right? The total number of turns on the solenoid is N. Now here I have marked minus L and here I have marked plus L, and through the center this I will call as the origin. So that from here to here the length is L, and from here to here another L. So that the total length of the solenoid is 2L. Now I am going to define small n as capital N by 2L, which means N stands for the number of turns in unit length. This is the total number of turns. I divided by the total length to get small n, which is defined as the number of turns in unit length. Now if I take a small section of the solenoid, a very small section of the solenoid whose width is just dx, so its width here is just dx, then the number of turns in this much width will be n dx, right? Because n is the number of turns in unit length. In a length dx, the total number of turns has to be n dx. Let this section of the solenoid be at a distance x from the origin, and we are now going to find out at a point P, we are going to find out this total distance I am going to take as r. So we are now going to find out the magnetic field at point P. This point P is along the axis of the solenoid, okay? Along the axis of the solenoid. Now if you take the small section here, it is now considered as a circular loop like this. A circular loop which is a portion of that solenoid of thickness dx. And for a circular loop along the axis at a point P, we know the magnetic field along the axis is given as mu 0 I r square by 2 into r square plus x square the whole raised to 3 by 2 from last chapter. So the radius of this loop is capital R. Okay. Now here I need to make a few changes. For a circular loop, if your circular loop is here, the x is the distance from the center of that loop to the point P. So from the center of the loop to point P would mean we need only this distance. And this distance would be what? Total R minus the x, because we have taken R from the origin. This distance would be totally R minus x, because from here till here is R, from here till here is x. So from the center of the loop to this point P would be R minus x. So here we need to replace this x with R minus x whole square, close the bracket, and 3 by 2. Also, this was for a single coil. Okay. If this coil had, let's say, it's got a width dx. So we decided that the total number of turns in that width will be n dx. So that means this is just for a single turn. If the total number of turns is this, we need to multiply it with n dx here. So this is r for us. So I hope you understood the changes that I made. In mu 0 I r square, no change because r is the radius of that coil. 2 into this x is the distance from the circular coil to the point P where we are finding the magnetic field. So we need this distance. That means it is r minus x, and that's what I included here. Then for a single turn is that expression. We decided that in this width the total number of turns will be n times dx, where n is the number of turns in unit length. Now here, if I take this distance r to be really large, that is point P is at a large distance from the center here, from the origin here, then I may say that r is much greater than the radius of the coil. R is also much greater than that small distance x here. So x is much smaller than r, and r is much greater than capital R. So if I take that r much greater than capital R also much greater than capital X, then in this equation I may neglect this r and this x in the denominator. So I will write B axial is equal to mu 0 I, I'll write on the other side. So here we will write B axial is then equal to, here, mu 0 I r square into n dx. Into n dx divided by 2 into, we have neglected this, So we have r square raised to 3 by 2. So that 2 and 2 will get cancelled, and we have 2r cube because we neglected this and this. Okay. So then we have from there I told you I want the constant in magnetism to be mu 0 by 4 pi. So I need to multiply by 2 pi and divide by 2 pi. Before that, to find the total magnetic field at P because of the whole solenoid, this what we've got here is only because of this small element dx. Okay. So in order to find the whole magnetic field, then B total magnetic field, we could call this as dB, the small magnetic field that is produced at P because of this small element dx. Now if you want to find for the whole solenoid, then we need to, this is total field, mu 0 by 2r cube. On top I have I r square into n. I need to integrate the dx starting from minus L to plus L. So minus L to plus L. Okay. So this is equal to mu 0 I r square into n divided by 2r cube. After integration, dx is x between the limits minus L and plus L. Now this will be upper limit minus the lower limit. So upper limit, when it takes, it will be plus L, minus of minus, another plus L. So that will be the total length 2L. So this is equal to mu 0 I r square n into 2L divided by 2r cube. Okay, so that is the expression. Then so this is the B axial total because of the whole solenoid. Now I told you I want that mu 0 by 4 pi because that's the constant in magnetism. So B axial I may write as mu 0 I r square n into 2L divided by 2r cube multiplied by 2 pi on top and divide by 2 pi because this will give me the 4 pi, and only if I put the 2 pi on top I have not changed the value. So I may write this as mu 0 by 4 pi. Then this pi r square you know is the area. So if pi r square I am going to replace as area. What is n into 2l? N is the number of turns in unit length and 2l is the total length of that solenoid. From here till here it is L. There is another L till here. So total length of the solenoid is n into 2l. Total length is 2l. So if I multiply n into 2l, I should get the total number of turns capital N, because this is number of turns in unit length multiplied by the total length of the solenoid. So that's what I'm going to replace. This is I here. Then the pi r square I'll write as A. Then this n into 2l I'll put as capital N. Then there is a 2 here divided by r cube. This NIA, as we know, is the magnetic dipole moment. So the final equation will now be, B axial is equal to mu 0 by 4 pi. I'm replacing NIA with magnetic dipole moment. So 2m divided by r cube, where m is a dipole moment and B axial is the other vector. So you will see that this is very similar to or analogous to our equation E axial as 1 by 4 pi epsilon 0 2p by x cube, where x is the distance of the point P where you are finding the electric field from the center of the electric dipole. Here also you will see that m is the magnetic dipole moment NIA and r is the distance of point P where along the axis, this point P is along the axis, you are finding the magnetic field at point P. R is the distance from the center of the solenoid to the point P where you are finding the magnetic field. So you see this whole solenoid we now proved behaves like a magnetic dipole whose dipole moment is given by NIA. So that was the third topic in your textbook. Okay. What we now have is the Earth's magnetism. In this chapter, the important topic that we have is the Earth's magnetism. Okay. So here, the origin of the Earth's magnetic field, it's still under study. Right now what we believe is that the Earth, the core of the Earth as you know is hot and molten, and the ions of iron and nickel, they in the molten form, they give rise to circulating currents because they are ions, they are charged particles, and because of the rotation of the Earth, the core is molten and they give rise to circulating currents. And as you know, any circulating current which is in a circular loop will have its own will behave like a magnetic dipole having its own magnetic field. So the molten form of the ions of iron and nickel at the core of the Earth will give rise to circulating currents, and which makes the Earth behave as if it has its own magnetic dipole and the magnetic field lines of the Earth. So it behaves as if this center, the core of the Earth, has a magnetic dipole. Then, so if I draw the Earth, let's say this circle represents the Earth. As you know, I am drawing this axis passing from the geographic north and the geographic south, which is called the geographic axis. So this line that joins the geographic north to the geographic south is called the geographic axis. Now, if you look at the magnetic field lines of the Earth, you will see that the axis, that is the magnetic north, and the magnetic south, the line joining the two is called the magnetic axis. This is not aligned along the geographic axis. they maintain an angle around 11.3 degree. Now, so the magnetic axis of the earth and the geographic axis of the earth are not in the same direction. The magnetic axis is tilted with respect to the geographic axis around 11.3 degree. Now what the scientists have discovered is that the magnetic north pole is actually not in the same place always. Every year it keeps shifting. Right now it is somewhere. If you look at this picture that I downloaded, you will see that the magnetic north pole has been shifting from close to Canada. It's now shifting towards Russia. In 2020, they've shown the magnetic north pole in the Arctic Ocean and the magnetic south pole in the Antarctic. So you will see that this magnetic north pole it's not at a constant place. And because of that, that's why I told you this angle will keep changing. Also, the distance between the magnetic north pole and the geographic south pole is around 400 kilometers now. That will also keep changing. So this earth, our earth behaves as if there is it has its own magnetic dipole, I told you. And actually, if you look at the magnetic field lines of the earth, the field lines of the earth come into the earth at the magnetic north pole like this. And from here, from the south pole, the magnetic field lines leave the earth. Now for a bar magnet, you know that the magnetic field lines enter through the south and leave through the north, right? So here what happens is, since the magnetic field lines are entering through the north pole here, is entering here, we should then come to the conclusion that this is actually the south pole of the earth, close to the geographic north. And since the field lines are leaving like this end, this pole that we call the south pole should actually be the north pole, right? Because that's how the magnetic field lines of the earth is behaving. So close to the geographic south, we should have the north magnetic pole. Close to the geographic north, we should have the south magnetic pole. But when the nomenclature was given, it was given as magnetic north here because if you suspend a bar magnet or your compass needle, you know what a compass needle is. You must have seen that horizontal circular dial. It will have a needle there, one end of which is the north pole and the other end is the south pole. So if you allow the magnetic compass needle to rotate freely at any place, you will see that the north pole will point towards here because this is actually the south pole. So the north end of the magnet or the magnetic needle will be attracted towards the south pole, and this pole was therefore called the north-seeking pole. And because it was called the north-seeking pole, this came to be named as the magnetic north. Similarly, for the magnetic needle, if this is the south pole, naturally it will be attracted towards the north end of the magnetic pole here. So this was called the south pole because this was called as the south-seeking pole, and therefore it came to be called as the magnetic south. So remember, close to the geographic north, we actually have the south pole, and close to the geographic south, we have the north pole. But the nomenclature is such that this is the north magnetic pole and this is the south magnetic pole. Simply meaning this is a north-seeking pole. The north end of the magnetic needle will always point towards the magnetic north, and the south end of the magnetic needle will point towards the magnetic south. Okay. So, now in order to find out the direction and magnitude of magnetic field at any place on the earth, suppose we are in Kochi here at my place. If you want to find out the earth's magnetic field at a place, both in magnitude and in direction, we need to know three elements. The three elements are called, one is called the angle of dip. The first one is called, one second. Okay, the first one is called the angle of declination. One second. I think you can see clearer now. The first thing that you should know is the angle of declination, and then the second element is the angle of dip, and the third element is called the horizontal component of the Earth's magnetic field. If you know these three elements, then you will be able to easily find out the magnetic field at a place on the earth, both in magnitude and direction. Now, if you look at this diagram here, you will see that the earth, they have shown with, one second. You will see that they have shown the earth here. These lines are called the longitudes and these are called the latitudes. Okay. Now, if you look at this black line here, this black arrow that's given, it is the line along the longitude. You will see that this black arrow points towards the geographic north. I told you that the geographic north and the magnetic north do not coincide. They are apart from each other around 400 to 800 kilometers right now. So this is the geographic north, and what they marked here is the magnetic north pole, which I told you right now is in the Arctic. So this black arrow that they've shown here actually is a line drawn along the longitude towards the true north, which is the geographic north. And this red line here is at this place. If you suspend a magnetic needle, the north pole of the magnetic needle will naturally point towards the magnetic north here, because I told you what we call as the magnetic north pole is actually the south pole, the south end. So the compass needle, the north end of the compass needle will now point towards this magnetic north pole. Okay. This angle between that is what you call as the angle of declination, represented by capital D. So if you look at this figure, you will see, I think it's clearer to you. This is the true north, which is the geographic north. And this is the magnetic north pole, that blue dot there. So this is the true north, the geographic north, and this is the magnetic north pole of the earth. This line that points towards the true geographic north, that is this green line here. And if you suspend your magnetic needle at this place on the earth, you will see that its north end or the north pole will point towards the magnetic north pole. So the angle between these two is what you call as the angle of declination. So angle of declination is simply defined as the angle between the true north or the direction towards the geographic north and the direction of the north pole of your magnetic needle, the direction in which it will point at that place. The angle between these two directions is what you call as the angle of declination, capital D. Here this diagram shows you this is a true north, this is the magnetic north. Angle between the two is what you call as angle of declination at a particular place. Now if you look in this diagram, so here in the textbook they have defined it as the angle between the geographic meridian and the magnetic meridian. Let me explain to you what are these meridians. Now, if you actually cut out a circle, can you see that at this place you have this longitudinal circle here. So from the earth, if I cut out a vertical plane like that, where this circle is the longitude circle, can you see the longitude is circular here. So if I cut out a plane, vertical plane from the earth, which is containing the longitude circle, and this is the axis of rotation of the earth, about which the earth is rotating. So any vertical plane which contains the axis of rotation and the circle, the longitude circle, that is called as the geographic meridian at that place. So at this place, this will be the geographic meridian. Okay. Similarly, if I look at the earth, it will have the magnetic field lines. So at this place, you have the north pole. This is the north pole, and you have this is the north pole, magnetic north pole, and this is the magnetic south pole. So you have these lines, imaginary lines, passing from the north pole here. That is, your lines are entering here and leaving here. So you have these imaginary lines coming out of the north pole here and entering here. So if I cut a plane which contains these imaginary magnetic field lines, a vertical plane that passes through that place, that is called as the magnetic meridian. The angle between the geographic meridian, which is passing through this, and the magnetic meridian in this direction, that is what you call as the angle of declination. So simply understand that this geographic meridian is a vertical plane in this direction, and the magnetic meridian is another plane, vertical plane in the direction of the magnetic field lines of the earth, and the angle between the two meridians is what you call as the angle of declination. Okay, so I hope that is clear to you. The second thing that we need to know in order to find out the earth's magnetic field is what you call as the angle of dip or angle of inclination I. For that, we have our next chart, where I hope it will be clear to you. Okay, look at this. Now, so the first one what we discussed was angle of declination. Now we have what we call as the angle of inclination, also called as the angle of dip. Now, if you look at this picture here, see, this is the earth, and these lines are the lines that show the magnetic field lines of the earth. Now, for the magnetic field lines, you will see that the compass needle, that this end is the north end, the darkened end is the north end of the compass needle. And naturally, since the magnetic field lines of the earth is going in at this pole, this is the magnetic north pole and this is the magnetic south pole. So the magnetic field lines of the earth are actually going in to this field, into the north pole, like this. Okay. Now, if you look at the surface of the earth here, you will see that these field lines are not parallel to the surface of the earth. They are actually coming in like this. Can you see that? So if you take up the angle of dip means, see, if you look at this diagram here, this is the magnetic needle that is dipping in towards the surface of the earth. Because we have the south pole here, the north pole of the magnetic needle will dip towards this, because your field line is coming like this. Now this is the horizontal, that is the tangent, the surface of the earth. This line represents the horizontal, which is the surface of the earth, parallel to the surface of the earth. So the angle through which your needle will dip towards the surface of the earth, that angle is what you call as angle of dip or angle of inclination. Here also, now look at this one. The field line, here the field line, the magnetic needle is in this direction. So if you draw a tangent to the surface of the earth, you will see that the magnetic needle is lying horizontal, is parallel to the surface of the earth. So the angle of dip is 0 at the equator. But if you reach the north pole here, magnetic north pole here, look at this diagram. This is the surface of the earth. If I draw a tangent, this is a tangent on the surface of the earth. At the magnetic north pole, you will see that this magnetic needle is perpendicular to the surface of the earth, and therefore the angle between the surface of the earth and the actual field, the total field of the earth is magnetic field of the earth will be 90. So at the poles, the angle of dip will be 90, but at the equator, the angle of dip will be 0. Okay, so basically I hope you've understood what is angle of dip. Your field lines are not parallel. If you look at these field lines, magnetic field lines that are coming into the earth, you already know that these field lines are not parallel to the surface of the earth. So you will see that at every point your magnetic field is actually making an angle with the surface of the earth. Now at this point you will see, let's see, look at this. At this point the tangent to the earth, this is the tangent, okay, and your angle, your magnetic field line is dipping, and this angle will be called as the angle of dip. How much angle does the magnetic field of the earth dip with respect to the surface of the earth, and that is what you call as angle of dip. Now here you will see that because we have the south pole here, the magnetic needle's north tip will be dipping down towards the surface of the earth. That is in the northern hemisphere. If you go to the southern hemisphere, we have the north end here, right, north pole here. So what will happen is, if you keep a magnetic needle, it will be the south end of the compass needle that dips towards the surface of the earth. So please understand that in the northern hemisphere, even though we call this as the magnetic north, please understand that it is the south pole actually, and therefore if you keep a magnetic needle, the north end tip of the north pole will dip, the north end of the magnetic needle or compass needle will dip towards the surface of the earth, towards the earth from the surface of the earth, and that angle is what you call as angle of dip. But if you come to the southern hemisphere, because we have the north pole here, even though we call it as the magnetic south, we have the north pole here, and therefore your magnetic needle, the south tip will dip towards the surface of the earth, and that how much it dips from the surface of the earth is what you call as the angle of dip. Now this diagram actually shows you exactly what we have combined the two. You will see that, can you see that this is the geographic meridian, which I told you is the vertical plane which passes through the longitude circle and has the axis of the geographic axis. So this plane here is called the geographic meridian, and the vertical plane that passes through the imaginary field lines, magnetic field lines at that place, that is what you call as the magnetic meridian. This represents the magnetic meridian. The angle between the two meridians is what you call as angle of declination D. Angle of declination D. On the magnetic meridian, you will see that the Earth's field line. So if this is the surface of the Earth, if your Earth's surface is like this is the magnetic meridian that I drew. If the surface of the Earth is like this, your field lines are actually coming in like this. It's coming into the Earth like this, right? So these field lines are never parallel to the surface of the Earth. So if you draw a tangent to the surface of the Earth, that will give you the direction of the surface, and from there, how much does this field line dip from the surface of the Earth? That is what you call as angle of inclination or angle of dip. So here you will see that the field line, the magnetic needle is pointing in this direction. So this is the total field of the Earth B. It dips through an angle which we call as I, angle of inclination from the surface of the Earth. This represents the surface of the Earth. So this being a vector has two components, the horizontal component and the vertical component. Okay. So this is what we have. In your textbook also we have this diagram here. So angle between the two meridians, the geographic meridian and the magnetic meridian, is what we call as angle of declination. On the magnetic meridian, we have, on this magnetic meridian I told you, this is the magnetic meridian that contains the field lines. So the field lines of the Earth are never parallel to the surface of the Earth. They come into the Earth like this, which means these field lines dip at the surface of the Earth. The angle through which it dips from the surface of the Earth is what you call as angle of dip or angle of inclination. Okay, so we have, in the first one, what I told you is, if we have the geographic north here and we have the magnetic north here, and let's say this is the geographic south, we have our longitude circles like this. Okay, this is the equator we have, right? Now suppose we are talking about a place, let's say here. The line, this line that I have drawn is a longitude line which points towards the geographic north and which is called as the true north. It's called the true north. And this line that I am drawing here actually points towards the magnetic north. Angle between these two is what you call as angle of declination. In your textbook, what we have is a plane, vertical plane that passes through the longitude circle is called the geographic meridian, and a vertical plane that passes through the magnetic field lines at that place is what you call as magnetic meridian. Angle between the two meridians is what you call as angle of declination. Now you will see as you go higher up, now this is at this place, if I take this place here, this will be angle of declination D. At a point at the equator, this will be the angle of declination. So you will see, as you go higher and higher, at the equator the angle of declination is very small. As you go higher and higher to higher altitudes, the angle of declination goes on increasing. So in India, which is a country close to the equator, the angle of declination is small. But as you go higher towards the poles or higher latitudes, you will see the angle of declination will go on increasing. Then the second thing we discussed, the angle of dip. We know that if you have the surface of the earth like this, at any place, let's say this is the magnetic north and this is the magnetic south. Your field lines are now coming in like this, right? Like this. So you will see that this field line actually is not parallel to the surface of the earth. This is a tangent at the surface of the earth. The angle through which this field line will dip at that place is what you call as angle of inclination or angle of dip. So at the poles, you will see that this is the horizontal, the tangent, and the magnetic field line is perpendicular there. So the angle of dip will be 90 degree because this is dipping with 90 degree here. But at the equator, you will see that the angle of dip is 0. So in once more I'll show you. So if this is the surface of the earth, from the surface of the earth, the magnetic field of the earth, which is the total magnetic field, I call as BE. The angle through which this total field of the earth dips at that place is what you call as angle of dip or angle of inclination. Now this being a vector, I may take this as the horizontal component of the earth's magnetic field called as BH, which is parallel to the surface of the earth, will be naturally BE cos I. BE cos I, the horizontal component, and this is the vertical component BV, which is equal to BE cos I. So please remember that BH is parallel to the surface of the earth, but BV is perpendicular to the surface of the earth, and this is the total magnetic field of the earth. So we may write BH by BV will be equal to BE cos I by BE sin I, or BV by BH will be sin I by cos I, which is equal to tan I. That is equal to tan I. So BV, which is BE sin I, BH, which is BE cos I, BV by BH will be sin I by cos I, which is tan I being the angle of inclination or angle of dip. So this is all we need to know in this chapter. In this chapter we started with proving that a circular coil that is carrying current behaves like a magnetic dipole. Then we went on to derive an expression for dipole moment of a revolving electron. Then we went on to show that a solenoid also behaves like a magnetic dipole. Then we went into the Earth's magnetic field, the three elements that are required to find out the direction and magnitude of magnetic field at a place. The first one we discussed is angle of declination D, then angle of inclination I, and the last one is the horizontal component of the Earth's magnetic field that is parallel to the surface of the Earth, that is BE cos I. So if you know all these three elements, you can easily find out the magnetic field of the Earth both in magnitude and direction. Thank you.